In the quest to understand complex systems, two approaches have dominated scientific inquiry: reductionism and holistic models. Reductionism, which focuses on breaking systems down into their smallest measurable components, has yielded significant insights, particularly in fields like physics, chemistry, and engineering. By isolating variables and conducting controlled experiments, reductionism enables precise measurements and detailed analysis of individual components. However, reductionism encounters limitations when applied beyond the realm of observable phenomena, especially when it speculates about unobservable entities or forces. This approach can lead to a fragmented understanding that fails to capture the emergent properties and interconnected dynamics inherent in complex systems. In contrast, the triadic model offers a holistic framework that emphasizes the relationships and interactions between components within a system. Unlike reductionism, triadic models are not just conceptual tools, they are descriptive representations of how natural systems self-organize. These models map directly onto the fundamental ratios and patterns observed in nature, often referred to in the context of sacred geometry. By identifying and analyzing triadic relationships, sets of three interrelated observable phenomena, this approach provides insights into the higher order dynamics that govern complex systems. The fundamental logic of triadic relationships define how three object systems can maintain a state of balance or homeostasis. The principle underlying our proposal is that establishing these types of balanced homeostatic relationships is how the universe naturally evolved and established stable systems, such as stars, planets, and life. The logic shows how pieces can naturally fall into place, and the 22 patterns are comprehensive for three object systems. Our proposal aims to integrate the strengths of both reductionism and triadic holism into a unified scientific framework. This synthesis acknowledges the precision that reductionism brings to the measurement and analysis of individual components, while positioning triadic models as the overarching structure that captures the self-organizing principles of natural systems. One of the key strengths of the triadic approach lies in its ability to provide a nested structure within which systems can be understood at multiple levels of complexity. In this framework, a system is represented by a triad, a set of three correlated measurements or components that are in dynamic relationship with one another. Importantly, if a part of this system needs further exploration, it can be broken down into a subtriad. This subtriad delves into the finer details of the state it represents, offering deeper insights into how that specific component can be influenced or controlled. However, even as we drill down into the components through subtriads, the higher order triadic relationship remains paramount. The dynamics of the entire system are governed by the interactions within this overarching triad, which cannot be fully understood by focusing solely on its individual parts. The triads operate hierarchically, where the state of a subtriad is directly influenced by its role in the larger triadic structure. This nesting allows for a multi-layered understanding of natural systems, where detailed examination of components enabled by reductionism is contextualized within the broader self-organizing patterns described by the triadic model. The triadic approach goes beyond being a mere model. It is a literal description of how natural systems organize. Each triad corresponds to a specific set of equations and ratios, reflecting the inherent order within the universe. Sacred geometric ratios, preserved for our understanding for countless ages, express the relationships between components in a way that is both mathematically rigorous and deeply connected to the natural world. In this sense, triads are not abstract constructs, but direct expressions of the fundamental principles that govern the behavior of all systems. Whether we are examining atomic structures, ecological networks, or economic systems, the triadic relationships provide a framework for understanding how these systems organize, evolve, and sustain themselves. This approach focuses on how dynamics of the universe are inherently relational, with each component's behavior being shaped by its interactions with others within a structured triadic framework. How those interactions take place is best conceptualized in the concept of fields, in the line of Tesla's electromagnetic fields to Sheldrake's morphic fields, but governing all possible interactions. It is not our purpose to provide a mechanism for fields, but to describe how they explain empirical data and thus deduce how they operate logically. The fundamental critique of reductionism lies in its assumption that understanding the parts in isolation will lead to a complete understanding of the whole. This is where reductionism so often goes wrong, attempting to break fundamental measurements into intangible, immeasurable components to explain their behavior, instead of looking at those measurements as components of a broader system. While reductionism excels in providing precise measurements and detailed analysis of individual components within a system, its utility is greatly enhanced when integrated into the triadic framework. Reductionist methods remain most meaningful when they are situated within the broader context of the higher order triads that govern the system's overall dynamics. They allow us to drill down into the sub-triads, offering fine-grained insights into the mechanics of specific components. However, it is crucial not to confuse the elements of a related triad with sub-elements of one or more of its components. Failure to identify the correct three variables in relationship is the reason that most modern mathematics rely on all manner of abstract functions to explain correlated measurements that don't directly influence each other. In this integrated approach, reductionism continues to serve as a tool for detailed measurement and analysis, while the triadic model provides the overarching structure that explains how these components relate to one another within the system. The fine measurements of reductionism can be incorporated into the triadic ratios, enhancing our understanding of how changes at the micro level influence the macro level dynamics. The synthesis allows for a more nuanced understanding of complex systems, where both the detailed mechanics of individual components and their relational interactions are taken into account. However, the triadic approach challenges core reductionist assumptions by proposing that the true dynamics of a system cannot be fully understood without considering the relationships between its components. The higher order triadic relationships control the behavior of the system as a whole, and these relationships cannot be reduced to the sum of the parts. As taught in esoteric wisdom, the higher overcomes the lower. By integrating reductionism into the triadic framework, we seek to rebut the basic reductionist principle and offer a more accurate and holistic approach to scientific inquiry. This approach adheres to first principles. We know only that which we can measure. we respect the strengths of reductionism in providing precise measurements, but insist we situate these measurements within a relational structure that reflects the true nature of complex systems. The triadic model, with its emphasis on nested hierarchical relationships, offers a framework that is both descriptive of natural organization and capable of incorporating the detailed insights provided by reductionist science. The explanations of systems that it offers are not only well defined but easy to understand. This benefits not just human science directly, but improves the emergent capability of artificial intelligence. By aligning our syntactic and semantic patterns with logical patterns, it allows AI to understand, interpret, and act safely in complex situations. In summary, our proposal advocates for a synthesis of reductionism and triadic holism, where the fine measurement capabilities of reductionism are integrated into the layered relational structures described by the triadic model. This approach not only provides a more complete and nuanced understanding of complex systems, but also reflects the true nature of how these systems self-organize. By grounding scientific inquiry in the literal descriptive power of triads and their corresponding ratios, we can develop a more accurate and holistic approach to understanding the universe, one that respects both the details of the parts and the dynamics of the whole. I hope you've enjoyed this introduction to triadic systems. Please subscribe our channel. We look at all topics to identify triads and explain their dynamics, from physics to metaphysics, with hundreds of videos organized into playlists by topic on our page. Whatever your interest, triadic logic is for you. Unlock the potential of your own understanding.